Welcome to the return of live lecturing in Math372. This should be lecture 20. So what I want to do today is I want to go over some of the gems from the proof of the Riemann mapping theorem. So to be brutally honest, I'm not too upset that I was too sick to actually go through and do the analysis proofs on the board. Those are somewhat better to read at home carefully and to see as an application of why we spend all of our time proving these results in real analysis. So a lot of the proofs break down into two parts. There's the complex analytic part, which is very different than what's true for real variable functions. And then there's just standard results about analysis and convergence. Things about when do sequences of functions converge, how do they converge, what do they converge to, things like that. The method of exhaustion, finding dense sequences of points, doing things at these dense points, and then propagating to other points. So a lot of that stuff is often called abstract nonsense, and you can apply this in almost any setting. But then there's this few parts where complex analysis is very different. So I don't think we ever explicitly state this in the book. So what I want you to do is I want you to do the Riemann mapping theorem on R. So this is not in the book. What do you think the Riemann mapping theorem should be for the real line? What statement would you like to, and the statement may be wrong. What would you think should be the analog of the Riemann mapping theorem?
I guess any open, interconnected open set of R, which is just any open interval, so it's not all of R.
Okay, connected subset of R that is not R is what?
Is whatever the word is to the unit interval.
So in complex analysis, we say conformally equivalent, which means that there is a differentiable function, infinitely differentiable function, function who has an analytic series expansion. What do we want here?
Maybe bi-differentiable. So
Bi-differentiable is by differentiably equivalent
What does that mean?
that the function and its derivative are both differentiable.
Okay.
I'm not sure if this word exists, but if not, you can email Oxford and get credit. Is bi-differentiably equivalent to 0, 1, is that what we'll call it? And so there's a lot of things to decide here. Do we think that the correct analog is bi-differentiably, or do we think that it should be something stronger, that may be infinitely differentiable?
Well, we can make it that.
Well, we can see. So the first question is, what are the possible sets that are open and simply connected and not all of R? Open intervals. Is that really the only thing we have? Yes. So this is definitely a well-known word, boring, right? If you think of the generalized Stokes theorem, if you look at the Stokes theorem in one dimension, it's boring because you're integrating from a point to a point. So here it's boring, only have open intervals. We can handle if it's an open interval to an open interval, what can we do this with? You should, shift and scale, translate and dilate. We can make it infinitely differentiable. We can make it analytic. Okay? What if we dropped the condition that it had to be a proper subset of R? So what if it was all of R? Okay, so let's say now we want to map R to 0, 1. Okay, so maybe inverse tangent. I was thinking of inverse tangent is I think the good one to do here. Now, will this be different? Will this be differentiable everywhere? And what about the inverse? Because is the plot of inverse tangent, is it like this? I'm trying to think. Comes in here and then goes like this maybe? Is it something like this? So the question is, if this is the case, what's going on right at the origin? But the derivative of arctangent is definitely 1 over 1 plus x squared. So the derivative here is going to be fine. So I'm not drawing the picture well. And then we'd have the inverse function would be taking the tangent. And will the tangent function have derivative that'll be fine everywhere in 0, 1? Yeah. So we can actually greatly extend this. So if we're looking at this in R, this is not an amazing theorem. The problem is because there's not that many interesting sets to look at. And this is the whole point of why you need to increase your dimensions. If you only look at one-dimensional objects, you don't have enough freedom to see things. Once we get into the plane, we have the ability to see things. And just to remind you, the generalized Stokes theorem. The integral over the boundary of C of omega is the integral over C of d omega. Have we written this in class before, early in the semester? Right, so essentially the derivative of the boundary becomes the region, and then the function goes to its derivative. And you have to interpret what these mean appropriately. And if you're in one dimension, if you have an interval, you only really have the 2 endpoints. It's the fundamental theme of calculus. If you talk about then a closed curve, we often want to have a closed curve. Well, the only closed curve you'll have is the interval that's just 1 point. And if you're integrating over something that's just 1 point, Stokes' theorem is not going to be that exciting. Okay. So they broke the proof of the Riemann mapping theorem up in a very nice way. They first said, here's Montel's theorem, and here's a theorem about injective functions. And then once we have all this machinery, then the Riemann mapping theorem isn't that bad. Because we can basically assume that our set is a nice subset of the unit disk, and then work from there. And Montel's theorem was split into 2 parts, a part that was using real analysis and a part that wasn't. So I will put this here so I remember. So this was Montel. So assume you have a family F of holomorphic functions uniformly bounded on compactor. How many of you have seen the phrase on compactor? I don't think the book uses the phrase on compactor. Yeah, by lecture, okay. So I don't know if this is an example of language has just changed since I was a kid. I've always heard the phrase on compactor to just basically mean a nice way of saying on compact sets. Just a little faster way of saying that. Okay. Now, yes, you have to spend a little bit of time saying what you mean by on compactor, but you only have to hopefully say that once. So then we have 2 results. The first is F is equicontinuous on compactor. And then the second is I think F is normal. Yes, F is normal. So a subsequence converges uniformly on compactor, not necessarily to something in F. And the second part here is just a result from real analysis. This is true in great generality. The first part, that F is equicontinuous on compactor, that's different. And for that one, we do need complex analysis. So the proof of it uses one of our favorite results. So proof of 1, Cauchy's formula. So I know we're in the Riemann part, so Cauchy really shouldn't be getting too much credit for this because we've already given Cauchy credit for this. Why is Cauchy's formula so amazing?
You get information about everything inside.
You get information about everything inside just by knowing information on the boundary or information in one region. So if you know, for instance, that the function f is bounded, you can propagate that to information in other places. You could also use this to get information about derivatives. And so the idea is, if we want to look at f of z minus f of w, this is 1 over 2 pi I integral over any closed curve gamma of f of zeta, and then 1 over zeta minus z minus 1 over zeta minus w d zeta. And now the only challenge is to figure out exactly where we want to put things. Okay? So this is where the proof becomes a little notationally involved, but in terms of ideas, it's not that bad. If you look at what's going on here, well, if I just look at this difference, I get zeta minus w minus zeta minus z. Okay, that's going to look like a z minus w, which I can pull out. So this would be a w minus z, then 1 over 2 pi I integral over gamma f of zeta over zeta minus z zeta minus w d zeta. And now if I want to show that this is small, if w is close to z, well, if w is close to z, I'm going to be small because of this. All I have to do is show that this part can't be too large. F is bounded. And so as long as I integrate over a sufficiently small region, this is going to be OK. Well, we've got to be careful. What's the danger here? Zeta gets really close to z or w. Now, normally what we'll do is we'll take zeta to be a circle about z. So then if w is really, really close to z, it shouldn't be too close to zeta. So frequently what we'll do is we'll say, look, imagine here's z. Take a circle maybe of radius 2 epsilon. Or maybe we shouldn't do epsilon because we'll be confusing. That looks small. Maybe radius 2r. And then we'll take another circle inside of this of radius r. And we'll choose w to be in that smaller circle. And then because z and w are inside a circle of radius r, the best case for w to be close to a point zeta is if w is right on the boundary. And then we just continue. So what's the closest w could be to a zeta? R can't be closer than r. So the denominator here is going to be, best case scenario, what? So what's the smallest the denominator could be? 2r squared. So you're actually being clever. If you weren't clever, instead of saying 2r squared, what would you say? Yeah, you would say r squared. But you notice, well, I know z is forced to be 2r away from zeta. So this has to, in fact, be exactly 2r. And then this other one has to be at least r. So it's going to be at least 2r squared. If you had just done r squared, that would have been fine as well. So we know that this denominator can't be too small. Now, we're going to be sending potentially r down to 0, but that's fine. We have some freedom over here. So we would get the absolute value of f of z minus f of w will be less than or equal to z minus w in absolute value divided by 2 pi. Over here, we'll get a 2r squared. And then f is bounded. So I'll put this to mean the largest value of f. And then what's the perimeter of gamma? 4 pi r. So the 4 pi will cancel with the 2 pi and the 2. The r cancels with the r squared. And this is going to be z minus w times the maximum value of f divided by r. So if I want this to be less than a certain amount, if I want this to be less than epsilon, well, this is clearly going to be less than or equal to delta absolute value, maximum of f over r. And if I want this to be less than epsilon, I just need to take delta to be less than epsilon over r, so r upstairs. So this gives me an opportunity to talk about a subtle point. Is this correct?
Unless the function is 0.
So here's the question. What if the function's identically 0? Is this correct? How do we interpret this then? Do you interpret this as saying any delta works?
Yeah, delta times 0 is less than any epsilon, so yeah.
I'm sorry?
Well, if the magnitude of f is 0, delta times 0 is always going to be less than epsilon.
Correct. But I'm saying, but we're now saying we need delta less than r epsilon over 0. So what some people do, just to be a little bit safe, is in a situation like this, always just put in a +1. Now you don't have to worry, is it 0 or not? And it gives you a little bit more of a gain. The other thing that's extremely important to note is, I think I make some remarks about this in the lectures, I like to put subscripts on if I'm working on a compact set, K. I will put a subscript K to say that this norm is coming from K. We are looking at what's going on. F is uniformly bounded on compactor. So we've fixed a compact set K. So really, this is not over omega. I should put a subscript K throughout to remind ourselves that this is the bound on the magnitude of F that we get coming from the compact set K. And different compact sets K could give us different bounds for F. Okay? But it doesn't really matter, because all we're trying to do is we're trying to show F is equicontinuous on compactor. You fix a compact set K, and you give me an epsilon, then there is a delta that depends only on epsilon and K such that. So it's okay that this delta depends on all this. So if you want, really, we should even call this delta of K to remind ourselves that we're doing everything on this one compact set K. And this is what we do not have in the real case. We do not have a situation like this. Okay, any other questions on this part of Montel's theorem? So the book has a nice function to consider. They said, look at fn of x is sine nx. Looks like a nice function. Maybe I'll study this on maybe the interval -1, 1. What do you get if you take the limit as n goes to infinity of fn of x? So what does this mean?
Like a really dense. I don't know if that's like a ton of.
Well, does the limit exist?
I don't think so.
Or does the function just oscillate more and more and more? Are there any places where the limit exists?
At 0.
At 0. So the limit exists at 0. Any other places where the limit exists? So if it exists at 0, it will also exist probably at plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. Actually, no. What if we look at what's going on at pi?
Or you're jumping between 0 and 1 then.
So here would be jumping between 0 and 1. Now, unfortunately, we're between -1 and 1, so pi doesn't exist. But I could look at pi over 4. And then at 4n, I would get the sine of pi, which is -1. At 8, I would get the sine of 2 pi, which is 1. So there's definitely points where we can clearly see the limit doesn't exist. It doesn't exist, I believe, at essentially every point. Does not exist for most x. Does this distress you? Are these nice functions? Are they continuous? Yes. Are they differentiable? Yes. Are they infinitely differentiable? Yes. Are they analytic? Yes. Are they uniformly bounded on compactor? Yes. They satisfy all the conditions in Montel. Right? So here's a family of holomorphic functions. Well, by holomorphic we'll mean analytic. Right? We're going to use our dictionary. They're uniformly bounded on compactor. So this satisfies conditions of Montel. Satisfies conditions of Montel, not the conclusion. So the whole point of this is to show you how different real analysis is from complex. And the fact that we are crucially using, when we use Cauchy's theorem, something of complex nature. So what goes wrong? Why is it not equicontinuous on compactor? And so the problem is, because this function is oscillating so much, if you give me any epsilon, there is no delta I can take because my function is going to oscillate so much that I can get 2 points that differ by a great amount. If I was writing an exam question, this would probably be a really good exam question. Prove that this family is not equicontinuous. It's oscillating too much, so you take epsilon to be a half, and I can get it so that there'll be 2 points very, very close to each other that when they're multiplied by an n, one is sent to basically something very close to pi, and one is sent to something very close to maybe 2 pi. So what's going on? What's wrong? Or is just complex really different than real? Complex is really different. Oh, sorry, really, no, bad sentence. I'll blame the drugs. What would happen if we looked at the complex analog? What if we looked at fn of z is the sine of nz? So this would be e to the I nz minus e to the minus I nz over 2i. Is this uniformly bounded? Say very close to the origin. So what would be a good value of z to take? Something imaginary. So if you take z to be pure imaginary, this would become e to the minus n, and this would become e to the positive n. So if you take just z to be I. Well, I is not close to the origin, but we could take I over a billion, and then take n to be a billion squared. So if we take z to be pure imaginary and very, very close to the origin, then if n is very, very large, this function becomes enormous. So this is the problem, is the family is not uniformly bounded on compactor. So when we look at the complex analog, things break down. Okay, any other questions on Montel's theorem? Okay, so the next one is the one-to-one theorem. Okay, so theorem. So we have a holomorphic family of one-to-one functions, Fn. I'm going to assume if I need to assume anything about the limit. Nope. That converge uniformly on compactor. to f, then f is either 1 to 1 or f is constant. So what's nice about this theorem is you're essentially asking what properties are preserved in the limit. So if I start off with a sequence of functions that have a property, will that property be kept throughout? We've seen before that you can go from a less than to a less than or equal to in the limit. That being strictly less than is not preserved, but being less than or equal to, that's different. Here the question is injectivity. If you start off as a sequence of injective functions, in the end, will you still be injective? Can you give me a sequence of injective functions that converges uniformly on compactor to a constant function? Okay. So let's let fn of z be z of n. That works. You can try to make it a little bit more falutin by having like 1 plus, yeah, but this is the best way to do it. As n gets very, very, very large, everything goes to 0. So this tells us that we do have to be careful that it is possible that in the limit, our function may not be injective. So one of the whole points of the Riemann mapping theorem is we're going through these constructions, and we're getting a sequence of functions. And at the end of the day, we want to find a sequence of functions that has a convergent subsequence, and in that convergent subsequence, we're going to get a new function. And we want this new function to be 1 to 1. And we want this new function to be onto. And it'll turn out that if the function is not onto, we can expand it and make it a little bit more onto. And there's going to be some kind of maximality principle going on. So we agree that we have to be concerned that the limit may not contain the 1-to-1 property. If it's 1 to 1, what do we know about the first derivative? It's not 0. So this was one of the really nice results we had about injective functions. The first derivative is not 0. Without loss of generality, we're going to eventually have our set living inside the unit disk, and we can always adjust it so it maps 0 to 0. So the Taylor series will always start off as just A1z. And this will tell us that that A1 will be non-zero even in the limit. So proof. Assume f is not constant. Because if it's constant, it's really not that much to show. Okay? So what does it mean if it's not constant? There exists z1 not equal to z2 such that f of z1 equals f of z2. Okay, so we know that there have to be 2 points like this. Is the table okay? Or okay, just making sure, don't want to lose more students. So let's define gn of z to be fn of z minus fn of z1. And then in the limit, just g of z will be f of z minus f of z1. So in situations where these limits exist, we can define them thusly. We know g has 2 zeros. This is 0 at z1 and z2. And what kind of zeros are these? So there's a nice word to describe what kind of zeros these are. Isolated. If g had a non-isolated 0, then what would that mean? That would mean there would be a sequence of other points converging to z1 or z2 where the function's always 0. And then we have our wonderful result from complex analysis that if you're 0 along a sequence that accumulates inside, then you must be identically 0. And if you're identically 0, you're constant. We're assuming you're not constant, therefore these are isolated. Do not feel sorry for the zeros that they're alone. It's good for them. Okay? What about gn? How many zeros does gn have? Just one. Could it have a 0 anywhere else? If it was 0 some other place, say it's z3, data dream, then f of z3 minus fn of z1 would be 0, so fn of z3 would equal fn of z1. But because fn is injective, that means z3 equals z1. So by the injectivity of fn, the only 0 here is at z1. The only 0 here, oh no, can't say only 0, this has at least 2 zeros. It could have more, and these zeros are isolated. So what theorem do we know that helps us count zeros? Or what approach? The argument principle. It's amazing what a constant function can do for you, right? So if we look at the integral of g prime of z over g of z dz, 1 over 2 pi I, and let's take a small circle centered at z2. And because it's an isolated 0, if the circle is sufficiently small, there's only one 0 inside here. Our limit is holomorphic. We have the abstract nonsense that gives us this. What must this integral equal?
Should be 0.
Not 0.
Should that be z1 then, or because it's only 0 and z1? Oh, g.
I'm doing g, not gn.
So then it's 1.
So it's 1. This counts how many zeros and poles does g have inside a small circle centered at z2. So here's z2, here's z1, and I'll take something like this with z1 far away. And because it's an isolated 0, I can choose a sufficiently small ball such that there are no other zeros. Now, by looking at this, I don't necessarily know how small that ball should be. But because it's isolated, there is some choice that works. Okay, what else should we look at? So this was looking at the integral of g prime over g. Yeah, do gn prime over gn. One of the standard tools we have in complex analysis is do the logarithmic integral. This is why I can do this lecture under all the stuff I'm on right now. I really don't have that many choices of what to do. When we're doing the analysis proofs, that's a lot harder. All right? So now I'll integrate this over gamma of z2 of gn prime of z over gn of z dz. What should that integral equal? That's the integral that should be 0 that you had remarked. Because gn has only one 0. It's only zeros at z1. And so this will always be 0. So we're almost done. We know that this equals 0. We know that this equals 1. All we have to do is show that in the limit, as n goes to infinity, this goes to this. And so what are we assuming? We're assuming we have a holomorphic family of functions that converges uniformly on compactor. Do we have to worry about what the radius is when we do the gn integral? Yes. How much do we have to worry? Do we have to worry a lot? We just have to make sure z1 is outside. Right? The radius here, it's not that bad. As long as z1 is outside, we're fine. Over here, do we have to worry about the radius? Yes, but it's one choice. So we choose a radius that works here, and then we just make sure that it's sufficiently small that z1 is outside. If it's not, choose something smaller. This one is still happy. These ones are now all happy. So we can find such a disk. You always have to just justify that you can find the disk that you want. You can, but you have to formally justify it. Now that we have the disk, we say, oh, our function converges uniformly on compactor. Here's my compact. Oh, I could even take my compact set to be the filled-in disk. I don't think I even need to take anything larger than that. And now, because it converges uniformly on compactor, is this denominator ever 0, and is it converging to 0 on this boundary? No. So I can show that this function here converges to this function here without any problem. These integrals must converge. I'm never dividing by 0. Everything is fine. 0 does not equal 1. exercise. And that finishes the proof. So now we know that at least if we have a sequence of one-to-one functions, if it's not constant, then it has to be injective. If you are the constant function and you map 0 to 0, what's your only candidate? The 0 function. So when we now go into the proof of the Riemann mapping theorem, we need to make sure we don't have the case where we end up with a constant function. Well, we're going to look at all functions that map omega to the unit disk, and we're going to assume omega starts off in the unit disk. Can you give me a function if, here's the unit disk, here's 0, and here's omega. Can you give me a function f from omega to the unit disk? I can think of two functions, and I want f of 0 to be 0. So this is one function, and there's another function you should be able to think of. Send everything to 0. You could, of course, also send everything to 0 over 2, 0 over 3, 0 over 4. But this proves that the set of functions is not empty. And if you look at the functions that have the maximal derivative, it's not going to be f of z is identically 0, f of z equals z beats it. So we're not going to have to really worry about that constant case. Okay. So when we now start doing the abstract nonsense of the Riemann mapping theorem, all right. So Riemann mapping theorem. Okay. So omega open, simply connected, not C, then there exists a conformal map F from omega to D that is one-to-one and onto. I forget, in our definition of conformal, do we assume that it's one-to-one and onto? Okay, I think our definition included that, but just in case, I'll state it again explicitly. All right, so this is the great Riemann mapping theorem. And the proof in the book breaks it up into 3 steps. The last step is just an algebra calculation, and it's a nice application of the Schwartz lemma. So step 1, without loss of generality, omega lives inside D. And this is a great simplification, because then it says we only need to study maps from subsets of the disk to itself. And then if you're trying to show that something is uniformly bounded, well, if I'm mapping a subset of the disk to the disk, what am I uniformly bounded by? 1. Okay? That's what's really nice about this. It's not hard to uniformly bound these functions. Right? So, again, I don't know, I can't remember how much the book emphasizes this point, but this is the beauty of it. It is no longer a challenge to show that the functions are uniformly bounded. Over there, amazingly, somehow that was not erased. Might even be foreshadowing of a great lecture. We had to think, how do we show that this is not uniformly bounded? And eventually we had the inspiration, let's try maybe z is pure imaginary, and if we take it really close to the origin, we can then compensate by taking n very, very large. And then maybe if we choose points appropriately, because the function's oscillating so much, we can get the difference to be larger than a half. But there's some work to go on here. There's no work right now to show that it's uniformly bounded. It's by construction. Okay? So now, proof. And it's basically as follows. If alpha is not in omega, all right, so draw on alpha not in omega, right. Then what we can do is we can basically define a logarithm. So we can define the log of z minus alpha. And because of this, it turns out that if you look at the values this takes on, if it takes on a certain value, it doesn't take on a value 2 pi I think, from it. And then you can show that if it takes on a value, say, f of w here, then, f of w plus 2 pi I, there's a small little disk around that it doesn't hit. And you just go through the analysis that it doesn't hit anything in a small neighborhood of this point. Well, if it doesn't hit anything in a small neighborhood about this point, then what I can say is, whatever f of omega is lies outside of here. What I'm going to do is I'm going to invert about this disk. And anything outside is mapped inside, and anything inside is mapped outside. So to make things as simple as possible to try to understand, where would you love that disk to be centered? At 0, yeah. So assume here's the point 0, and here's a small little disk. We don't get anything inside. And then here is f of omega. We can define a new function, g of z is 1 over z. If you were on the boundary of the unit circle, you stay on the boundary of the unit circle. Well, of course, assume this is the unit circle. I mean, why would it not be the unit circle, really? If you have absolute value greater than 1, you now have absolute value less than 1. If you had absolute value less than 1, you now have absolute value greater than 1. So this takes anything outside and moves it in. It takes anything in and moves it out. Boundary goes to the boundary, but we're not on the boundary. Is this function injective? Yeah, 1 over z1 equals 1 over z2, z1 equals z2. So we can now assume that our function omega is that omega lives inside the disk. So without loss of generality, omega is a subset of D, and we can assume f of 0 equals 0. How do we assume f of 0 equals 0? What if f of 0 was not 0? Yeah, we use these, these C alpha of z is alpha minus z over 1 minus alpha bar z. So if originally f of alpha was 0, not f of 0, then we just use this to translate. The book doesn't do this right now. The book then talks about maximizing the absolute value of f. What we could do right now is we could just do a rotation to make the first derivative positive. So the first derivative is non-zero. Why is the first derivative non-zero? It's injective. So f prime does not equal 0 as injective. We could just rotate to make f prime of 0 greater than 0. Let's say f prime, well, actually it's just true in general. F prime is not 0. Right? The book talks about maximizing the absolute value of f prime. We could just rotate each one of them and make each one of them real. Doesn't really matter. So we can go through all this. And then this is where you have the abstract nonsense coming in. So now we use Montel's theorem to find a sequence that maximizes the absolute value of f prime of 0. And then we say, of all of them, let's look at the one that has the largest possible value for f prime of 0. We know that this family is non-empty. Okay? Use Montel to maximize the absolute value of f prime of 0. Non-empty family as the identity is in it. Also trivially uniformly bounded. It's always nice when all of your conditions hold trivially, but you have to observe. When I teach operations research, one of the things we have to do is we have to decide how should airlines fly planes? How should movie theaters schedule showings? And the way all of this starts is you need to show that a schedule exists. And once a schedule exists, then you can use that as your starting point and you can flow to an optimal. How do you think you can you give me a schedule that exists for flying planes? Or for showing movies? That's valid, that will satisfy all the constraints. You don't want to have the same movie starting at the same time in different theaters. You don't want to have too many people getting out at the same time. There's a very simple solution to showing movies that will satisfy all constraints. Nope. Don't show any. Do nothing. That's your starting point. It is amazing what you can get from doing nothing. Then once you have a valid schedule that satisfies all these constraints, then you try to maximize profit. And you realize that showing no movies is probably not the best way to maximize profit. But it's a start. All right, we've got about 2 minutes left. So this is just enough time to finish the proof of Riemann because we do not want to split this into another day. So the last part is assume that our limit is not onto. So there exists an alpha not in f of omega. And then this is just a nice calculation. I'm going to just write it down in the interest of time. So g of w is e to the 1/2 log w. H of w is w squared. So this is the square root function. Is the square root function injective? So we're basically taking the angle and decreasing it. So will two things be sent to the same thing? No. The only way they could be sent to the same thing is if they had the angle of 0. And then because we're taking the square root, we're decreasing the magnitude. We're not on the boundary, so we're fine. So we have two functions like this. And now what we do is we look at this function f. I apologize for not memorizing this. C of g of alpha composed with g composed with c of alpha composed with little f. And this is in our family. So this means it sends 0 to 0. And then if we call this whole thing C inverse, or phi inverse, we get that f is equal to phi composed with f. And then if we take derivatives, we'll see first that phi maps the disk to the disk, but it's not 1-to-1. And the reason phi is not 1-to-1 is when we take the inverse. Well, the inverse of the C alphas are very easy. They're just themselves. What's the inverse of the square root function? The squaring function, coincidentally written right next to it. So this function phi is not going to be 1-to-1. So when we take the derivative, we get f prime of 0 by the chain rule is phi prime at f of 0, which is just 0. But I'm going to write it as f of 0 is 0 like this, times f prime of 0. So we get the absolute value of phi prime of 0, f prime of 0 is phi prime at 0, absolute value, times f prime of 0. But by the Schwarz lemma, this is less than 1. Why? Because our function is not injective. And the Schwarz lemma says it's strictly less than 1 unless it's blah, 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 blah. And now we get huge dividends from the Schwarz lemma. So this now means big F prime of 0 is greater than little f prime, which contradicts little f prime, little f being our maximal derivative in absolute value. What was the only assumption we made? The only assumption we made was that it was not onto. So at the end of the day, when the dust settles, the limit function must be onto. Okay, so this was, I definitely agree, blitzkrieg general overview of the Riemann mapping theorem. The details are in those 2 lectures you saw in the books. We are not going to use the mathematics of this itself in anything subsequent. And then we'll be doing a new topic on Wednesday. I will send you emails about that. All right.